In this video, we're going to talk about the pH scale and what the numbers in it mean. At this point, we've talked about what acids are and what bases are, and we said acidic solutions, the acids contribute a hydrogen ion, which then gets absorbed by water to become a hydronium ion. And we've said that basic solutions contain a high amount of hydroxide ions. And today what we're going to do is quantify those values in terms of pH. So if we look at water, and it's all based off of water being the solvent. So water itself is amphoteric. It actually acts as either an acid or a base, but it kind of acts as both at the same time on its own, just at a very, very small scale. Okay? So water, in a solution of water, it self-ionizes and breaks apart into the hydronium ion and hydroxide ions, but at a concentration of 10 to the negative 7th molar of each. So the water breaks apart into its components, so it has an equal amount of basically what you consider the acidic component and basic component, which is why we would call it neutral. So from this, we can establish an equilibrium constant for water. If we remember, the equilibrium constant is equal to the concentration of products over reactants, and they all have to be in the same phase. So if we write out the dissociation for water, we can see that it results in the production of hydronium ion and hydroxide ion. Notice that I drew the double arrow with a much smaller arrow going forward than going backwards. And that's because the K value for this is going to be very, very tiny, and most water remains in the undissociated form, or the associated form, and very little actually dissociates. So setting up the equilibrium constant expression for it, our Kw is equal to our hydronium ion concentration times our hydroxide ion concentration over our water. Now, since water is a pure liquid, and any pure solid, liquid, or gas can be removed from the expression, we just get rid of it. So our Kw is then just equal to the hydronium ion concentration times the hydroxide ion concentration. And if we look at what those values are for water, we can see that they're both 10 to the negative 7th molar. So 10 to the negative 7th times 10 to the negative 7th gives you 10 to the negative 14. And that exponent right there, 14, is what we get our pH scale. We say it goes from 0 to 14. That's where that number comes from. And we've said that the pH of neutral solution or water would be 7. Where that comes from is the fact that the pH is the negative log of your hydronium ion concentration. And you'll also see it written as H+, or H3O+. Consider them to be the same thing. Use them interchangeably when you're doing calculations. So if we take the negative log of our hydronium ion concentration for the water here, which is 10 to the negative 7th, we see that our pH is 7, because log means 10 to the what? So in this case, it's 10 to the negative 7th. So you'd have negative 7 as your log of that value, times the negative sign. So negative times negative 7 gives you a pH of 7 for water. And that's actually where we get the term, the idea that 7 would be neutral. It kind of doesn't make sense that the middle of a scale should have a value of 7 instead of like something like 5 or 10 or whatever, or 50. But that's where we get the number 7 as being a neutral solution. All right, so now that we've seen where the term pH comes from, we can expand upon that a little bit and describe a solution's pH in a couple different ways. So we can use pH, which is the negative log of your hydrogen ion concentration. We could also take a pH and convert that to find the hydrogen ion concentration, if that's what we know. We can describe the pOH, which is the same thing as pH except with respect to the hydroxide ion concentration, by using the negative log of your hydroxide ion concentration. Our hydroxide ion concentration is equal to 10 to the negative pH because, again, log means 10 to the what power? So if we're looking for the hydroxide ion concentration, 10 to the negative pOH would give you that value. One other thing to point out, because of the Kw of water being 10 to the negative 14, if we take the negative log of your hydrogen ion concentration and a hydroxide ion concentration, we come up with the pH and the pOH. And if we take the negative log of 10 to the negative 14, which is the Kw of water, we get the value of 14. And we also know that, again, the Kw of water, which is the product of your hydrogen ion concentration times the hydroxide, gives you 10 to the negative 14. So all this stuff looks like a huge mess, but basically what we can do is use if we know any one of these, we can figure out all of the other descriptors for the solution. For example, coffee has a pH of 5, and here it shows it over here. This solution clearly looks acidic, as if we look at the red particles as being your hydronium ion concentration, your hydronium ions, and your hydroxide as being your hydroxide concentrations being the blue dots, you can see that there is a substantially greater amount of red dots than blue dots, and that's because you're in an acid, and the pH scale is basically each step on the pH scale is a factor of 10. So like a pH of 5 is 10 times as acidic as a pH of 6, and a pH of 4 is 100 times as acidic as a pH of 6. So you have quite a different ratio of those two things to each other. Now, we said coffee has a pH of 5, so to determine the other values. Hydrogen ion concentration is just 10 to the negative pH. So if your pH is 5, then our concentration of hydrogen ions is 10 to the negative 5. Obviously, this is a nice clean integer, so it works nicely that I can just do it like that. Otherwise, you'd have to plug it in on your calculator and take 10 to the whatever the pH is if you did not have an integer. The hydroxide ion concentration then, because this value times your hydroxide ion concentration gives you 10 to the negative 14, we could say that, well, the hydroxide ion concentration is 10 to the negative 14 over and divide by 10 to the negative 5th. So we would have a concentration of 10 to the negative 9th molar. And then the POH is the negative log of your hydroxide ion concentration. So 10 to the negative 9, your POH then is 9. Now we could also have gone another way with this. Since we know the pH and the POH add up to 14, and we know the pH is 5, we then could know that the POH is 9. So knowing that the POH is 9, we could simply plug it to find the hydroxide ion concentration. We'd go 10 to the negative 9, and we would get that answer. So if you know any one of these variables, you can convert to the other ones by using any combination of these equations. So as we said, the pH is the negative log of your hydrogen ion concentration or your hydronium ion concentration. So we can also take that and go backwards. If we know the pH of a solution and we want to figure out your hydronium ion concentration for, say, doing a stoichiometry calculation, you can then just take 10 to the negative pH to determine that value and use that. On the other side, if we're looking at the basic component of the solution, we can look at the hydroxide ion, and when we take the POH, that's going to be the negative log of your hydroxide ion concentration. And again, the same thing as your hydrogen ion concentration. If you want to find that value from the POH, you can use 10 to the negative POH to get that value. Now, one thing that we know is the pH and the POH, when you add them up, you get a value of 14. And that's because the dissociation, or the Kw for water, is 10 to the negative 14th. So your hydrogen ion concentration, or hydronium ion concentration, times your hydroxide concentration will always give you 10 to the negative 14th. If you take the negative log of each of those components, you end up with negative log of H plus is pH, negative log of hydroxide is POH, and then negative log of 10 to the negative 14 is 14. So a very easy way to do a calculation is to say, okay, if I know the POH, say the POH is 6, then that means our pH would have to be 8. And then we could use the equations to go convert to anything else that we're looking for. So a sample calculation I'd like you to follow along with is, we all love coffee, and coffee has a pH of 5. So what I would ask you to do is to determine the hydrogen ion concentration, or hydronium ion concentration, your hydroxide ion concentration, and your POH. Those would be all the other ways we could describe it with respect to this pH scale. So the hydrogen ion concentration is 10 to the negative 5. And we get that because the hydrogen ion concentration is 10 to the negative pH, which in this case is 5. The hydroxide ion concentration is 10 to the negative POH. So we could say that if we know the pH is 5, then the POH would have to be 9 to make it add up to 14. So if the POH is 9, our hydroxide ion concentration would be 10 to the negative 9. So we can look at any of these concentrations based off one piece of information. Now, granted, we used integers here, which makes it nice and easy. We could just say 10 to the negative 5. If you have to plug in a different value, you just got to plug it into your calculator, and you'll get a not so clean number, but it all works just the same. All right, so now we're going to go over a couple practice problems from the homework. We'll select the 3 that you see stars next to, and then we have one more that's the numbers aren't quite as clean with. So the first one just asks you to determine the pH of a solution that contains a 0.0010 molar concentration of sodium hydroxide. Since sodium hydroxide is a strong base, we can assume that it's going to break apart 100% of the time. So that means that our sodium hydroxide concentration is going to be equal to our hydroxide ion concentration. So that's 1.0 times 10 to the negative third. That's just writing this in scientific notation, showing the correct number of sig figs. So then to calculate the PO, we can get the POH and then get the pH from that. So the POH is the negative log of that concentration which gives us a value of 3. Then, if we know that the pH and the POH have to add up to 14, you get a pH value of 11, and which makes sense because this would be a basic solution containing something like sodium hydroxide. The next problem adds one new layer of difficulty in that, well, the calcium hydroxide contributes 2 hydroxide ions for every formula unit of calcium hydroxide you have. So you basically have to take the molarity, and its effective concentration of hydroxide ions is going to be double what your concentration of calcium hydroxide is. So you get 2 hydroxides for every calcium hydroxide, and that gives you a molar concentration for the hydroxide ion of 0.10. Taking the negative log of that value, you get a POH of 1, and since the pH and the POH add up to 14, that gives you a value for the pH of 13. Now, if we're talking about a weak acid, they don't dissociate 100% of the time. So for this unit, we're going to give you percent dissociation to look at to determine it. In the next unit, we'll look at K values to determine this. All right, so assuming that acetic acid has a percent dissociation of 5.0, we can then say that effectively, if you have a 2 molar solution of that you get 5 moles of hydronium ions for every 100 moles of acetic acid that you have. So that gives you an effective hydrogen ion concentration or hydronium ion concentration of 0.10 molar. So that means that if you take the pH to get the pH, you take the negative log of that value, and that would give you a pH of 1.0, which then would have a POH of 13. So pH is 1.0. Now all of these numbers give you nice clean 0.01s or 10s and all that stuff. However, it's not always going to be that clean. If we have a solution with a pH of 5.28, and I ask you to determine the hydrogen ion concentration, your hydroxide ion concentration, and your POH, then you have to actually use your calculator and you can't just do it in your head. So if the pH is 5.28, a hydrogen ion concentration would be 10 to the negative pH. So 10 to the negative 5.28, you plug it in your calculator and you get 5.25 times negative 10 to the negative 6 molar concentration. In order to determine the hydroxide ion concentration, then we use this equation where the Kw, where the hydroxide ion concentration times your hydrogen ion concentration, is always going to be equal 10 to the negative 14th. So rearranging that, you get 10 to the negative 14 over 5.25 times 10 to the negative 6 gives us a molar concentration of hydroxide ion of 1.91 times 10 to the negative 9th molar. So then, using this value, if we were to calculate the POH, we would simply take the negative log of that concentration, hydroxide ion concentration, to get a value of 8.72. And just to check ourselves, we should be able to check that that's right because, well, this number and this number, your pH and your POH, should always add up to 14, which in this case they do. So these are just a couple different types of problems where we could add another layer in when describing pH or POH.